What's going on? I'm in my conference room doing physics right now. Today, we're talking about the Millikan experiment, the elementary charge, the charge of an electron or proton, and how we can use that equation. It's a pretty simple equation, but it was established or determined in an experiment known as the Millikan experiment. So, let's go ahead and talk about the experiment. Here's the deal. First thing you want to understand is its setup. Its setup looks just like this, okay? There was a sample of oil, and then it was put through an atomizer. An atomizer is something that like spews very tiny droplets out, right? Very, very tiny droplets, called an atomizer because it essentially just makes them like atoms, right? Like molecules, like boom, sprays this out. So it sprays it out into this mist, into this sample right here, and that sample eventually trickles down one particle at a time, or a few particles at a time, down into a detector system. This detector system has a detector which is like X-rays, but it doesn't matter for us. It's basically a camera. Imagine a camera that is so perceptive, so precise, it can look at individual droplets of a falling object. Now, that falling object, when it finally makes its way into this area, is subjected to two things. It's subjected to an electric field, which for our purposes just produces a force, an electric force on the object. Now these particles here are all kind of negatively charged because they've been spewed out and they're in this field. So by adjusting this electric field, or by adjusting the difference, the electron, the negative plate and the positive plate, we can get this object here to be repelled by this negative plate, okay? Now, the first force it's subjected to, obviously, the reason it falls down, we're going to exaggerate that force, is gravity. It's pulled down towards the middle of the earth. By adjusting this plate, or this parallel plate, we can actually apply that upward force up on the drop. We call it an electric force, or an electrostatic force. All right, so at some point, though, by observing this system, we will watch those drops stop moving. And when we see those drops stop moving through a calculation that we're not going to talk about, but through a calculation, we can determine, based on the mass of this object, we can determine the charge. We know exactly how repelled this object is because we know that this force and this force are equivalent when it's held at rest. We know that because of Newton's first law, okay? So when these two forces are equal, we know exactly what must the charge of this object be because it is repelled by this plate that we were tweaking with our little dial. Now, Millikan does this experiment and gathers the data, and what he determines is that the elementary charge of a particle, the charge of an electron or proton, is exactly 1.6 times 10 to the negative 19th, meaning if you have a whole electron, that electron is going to have that charge. Now, I can't have half an electron, at least in our class we can't, right? You get super nerdy, you get these particles that make up electrons, but I can't have half an electron. And so because I can't have that, I'm going to end up, this is what we call the elementary charge. So any charge on an object must be some multiple of this value. I can't have 2.0 times 10 to the negative 19th coulombs of charge because that's less than 2 electrons that have 1 point something electrons, and I can't slice electrons in half. That's why we give this name, and we call it the elementary charge. Now, along with this, there's also an equation we can use. That equation basically states this. It's Q equals capital N E. Let's break that equation down. This equation Q, that's a Q, is the total charge of an object. Now the total charge of the object is equal to this right number right here is the number, capital N is the number of electrons or protons slash protons based on protons, what you call the elementary charge. If you call it negative or the charge is negative, then it doesn't matter, okay? But if it's an electron, we would use E negative. If it's a proton, we would use E as positive. So this is the number of electric particles, right? Whether it's electrons or protons, charged particles, that's a big difference. E here is the elementary charge. That's the number that Roger Millikan discovered in his experiment. It's that 1.6 times 10 to the negative 19th, right? Now, if this is an electron, we already said, we would give this a negative 1.6 times 10 to the negative 19 coulombs. And if it's a proton, we would call it positive 1.6 times 10 to to the negative 19 coulombs. This is how we kind of keep track of these numbers. This is how we would interchange these in our equation here. Straightforward equation. Let's see how we can use it in practice. Uh-oh. There's an announcement. We'll ignore it, okay? Question 1 says, a balloon removes 200 electrons from hair, charging by friction. When that happens, the question is, what is the charge on the balloon / hair? So it's kind of a conservation of charge question to understand that whatever the balloon's charge is, the hair's charge is opposite that. But the balloon, it's my balloon, cool, takes electrons. So because it has electrons on it, the balloon's going to be negatively charged, and then the person's hair over here is going to have positive charges on it. Our job is to figure out exactly what is the charge here. So let's go ahead and use our equation. We know we're looking for the amount of charge. I don't know how much charge is there, but I do know how many particles there are. So in order to find the charge, I'm going to go ahead and say there are 200 electrons. And in this case, the elementary charge is negative 1.6 times 10 to the negative 19 coulombs, because I'm using an electron, and my charge will end up being negative. And so when I do that, when I punch this in my calculator, I end up with an answer of 3.2 times 10 to the negative 17th coulombs. That is the charge of the balloon, because the balloon was negative. All right, the balloon was negative. But in the beginning, I had a neutral balloon and neutral hair. So in order for this whole system to remain neutral, for charge to be conserved, if the balloon is negative 3.2, that's going to make the hair positive 3.2 times 10 to the negative 17 coulombs. Now my net charge is still 0. I haven't broken any laws of nature, and I figured out exactly what the charge is on that balloon after it was charged by friction. Let's try problem number 2. 2 says, if an object has a charge of something, positive 10 microcoulombs, that little mu means micro, and micro means 10 to the negative 6th. It's on your equation sheet, your area of constants. But the question is, how many more protons than electrons are in the object? Okay, so I know a charge. That charge is positive 10 microcoulombs. How many more protons? I'm using protons, so my elementary charge, it better be positive. Let's try it out. My equation, always write the equation, Q equals N. E for the proton, let's call it E plus. We can call it E plus because it's the elementary charge, but that elementary charge is going to be positive this time around. It's a video for you, Dino. All right, so the charge, 10 microcoulombs, let's call it 1 times 10 to the negative 6 coulombs. We want to make sure our units are in coulombs. I'm sorry, this is 10 times 10, right? Because the charge is 10 microcoulombs is equal to some number that I don't know times the elementary charge of a proton, 1.6 times 10 to the negative 19th coulombs. You can kind of see that when I take coulombs and divide it by coulombs, I'm going to end up with a dimensionless or unitless number. That's what N will be. All right, so in order for us to do this, I would divide both sides by my my elementary charge. So let's go ahead and do that. When I type that in my calculator, I end up with, this is a few more keystrokes that I am used to. 10 times 10 to the, I end up with 6.25 times 10 to the positive 13th protons. And why is it protons? Because the elementary charge I plugged in was the charge for the protons. That's a lot of protons, and that's not very much charge. So you can kind of see that as charge builds up, 1 coulomb is a ridiculous number of electrons. But nonetheless, this is the Millikan experiment. This is the outcome of the Millikan experiment. This is the equation we can use to track the number of electrons or protons that produce a specific charge. If you've got more questions, drop in the comments, ask me in class, send me an email. Until next time. See ya.